All right, Stanley Lake Physics. Welcome. You've already talked about how a current in a wire creates a magnetic field, which is so cool. And a changing current creates a changing magnetic field. Today we're going to go through that last bit of magic that magnetism holds to offer, which is that a changing magnetic field creates a current. Now that's just weird. That shouldn't happen. I mean, that's just strange that you can just have a changing magnetic field and that makes a current. So I have here a voltmeter, and I have here some coils of wire. What you'll notice is there's no battery. There's no place for a battery. So this voltmeter is measuring the voltage produced by this set of coils. And you can see nothing is happening right now. But if I take a magnet, and I take that magnet and move it through that coil of wire, magically we've got some current. That's just so strange. And if I don't move it, if I just have a steady magnetic field, there's no current. But if I move it a little faster, there's more current. And if I move it a little slower, there's less current. So let's see what happens if we have more wire. So if I take more wire and move my magnet, we're getting more current, and still more wire, still more current. And now let's see what happens if I take a stronger magnet. This is a neodymium magnet, very, very powerful. And if I move that in my coil of wire, you can see I get a lot of current. Oh, very powerful magnets. All right, next thing that I want to show you is this tube of copper. So that's all we've got here is a copper tube. It's hollow. And I've got two weights. One of them is magnetic, and the other is not. It doesn't stick. Copper, so this is my magnet. Copper is not magnetic. I can't get that magnet to be picked up by copper. It's not one of those materials that will allow me to do that. So I'm going to show you what happens if I take the non-magnetic weight and put it through this copper tube. So you ready? This is pretty exciting. All right, so I've got the non-magnetic one going through the copper tube. Gravity works. Yes. Let's look at that again, because that's pretty amazing. So gravity works. All right, that's the not magnetic one. Now let's take the one that's a magnet. And I'm going to put that through the copper tube. Let's try that again. All right, it's not sticking because it's a magnet, because copper doesn't stick to magnets. So something else has got to be going on here. So before I explain what's going on there, let's take another example. I have here two pieces of 3-foot long material. This is aluminum, and this is wood. These are two neodymium magnets. So definitely magnetic. This magnet does not stick to the wood, obviously, and it does not stick to the aluminum. So it will stick here, but it does not stick to the aluminum. So let's go ahead and have a race and see what happens. If I take these two neodymium magnets and race them down each of these objects. Okay, get them started at the same place. They're at the same angle. Okay, that neodymium magnet is not sticking to the aluminum. And definitely didn't stick to the wood. So what is happening? Well, you're actually getting a current produced inside this metal. So as our magnet moves down this metal, it creates a current in the metal, which then creates a magnetic field, which then attracts the magnet and slows it down. And so I'm going to draw you a little picture just to show that. this is our metal that our little magnet was moving down. When it's just sitting there, nothing happens. So there's no current produced. But when our magnet starts moving, now all of a sudden there's a current that's produced inside the metal, because even though the aluminum doesn't stick to the magnet, it's still metal, so it's a conductor and electricity can be produced. So let's say that this is the north end and this is the south end of my neodymium magnet. Then inside here, the current will produce a north and a south, which then sticks to this magnet. When the magnet then stops moving because it's stuck, there's no current produced anymore, and that magnet goes away. When that magnet goes away, it can go down the ramp a little ways. But when it goes down the ramp a little ways, it creates a current, which creates a magnetic field, which then makes this magnet stick. Then this stops moving. Then it turns off the current, which turns off the magnetic field. When the magnetic field turns off, it can start moving again. And when it does that, it goes a little bit further down, and it's moving, so north and south, creates a little magnet by making a current, which then makes it stick, which makes it stop, and then the magnet goes away, and then it can move down again. When it moves down again, it creates a current, which creates a magnetic field, which then makes it stick, and then the magnetic field turns off, and so on. So what you're getting here is the changing magnetic field caused by the magnet moving creates a current in the metal here that then produces a magnet that attracts it and slows it down. This doesn't happen in the wood because the wood can't make itself be magnetic. There's no current that happens in wood. It's an insulator, not a conductor. And in the eddy tube, the copper pipe, we couldn't produce it with the non-magnetic one. As it's moving through the tube, it doesn't create a current in the copper pipe. Only the magnet can do that, which is why only the magnet is slowed down.